I see we have Helen Kirk on the line. Okay, she'll be speaking to us about early results from the Keystone Survey.
Great, thanks so much for the invitation. I'm sorry I can't be there in person. It looks like there's a lot of exciting discussions probably going on over the lunch break and everything. I have a bit of a cold right now, so fingers crossed I make it through this talk without coughing too much for you. So I wanted to talk to you today about the Keystone Survey. This was PI'd by James DeFrancesco, also based here in Victoria at NRC. He sends his regrets that he couldn't be here for this meeting. So thanks to the excellent gas and ramps talks that we've already had this morning, you've gotten a great overview on star formation, a lot of the open questions, and how important ammonia is. So I won't spend quite as much time on that. But as you already know, there's lots of very interesting open questions in star formation. Some of those include how do stars and then clusters of stars gain their mass? What is the role of the filamentary structure that we're starting to see in these regions? And is it fundamentally different for high and low mass star formation? And what is the role of the larger environment on the structure that can form? And so we know that there's a wide range of size scales and time scales involved in the formation of stars. And that means that really you need a multi-tracer, multi-wavelength approach to really fully tackle these big questions. And I'm sure you've all seen these many spectacular large area continuum images, such as from Herschel over the last number of years. And certainly in the low mass star forming regions, they've really helped to push this picture that star formation is driven by filamentary structures, and you really don't get stars forming outside of the filaments. In high mass star forming regions, there may be a lot of additional things going on. We heard a bit about that already from Jim Jackson's talk this morning. So photoionization, for example, that he was talking about, among other things. And also we start to see these intersections of filaments, that are known as hubs. That may be very important for the formation of perhaps clusters of stars or high mass stars. And really to start to answer these questions about how the mass is flowing, you need velocity information. And that's where something like the GVT measuring ammonia comes in. You really need to see how the dense gas is moving and not just see where it is. So I'll talk a little bit about the hobby survey. I'm sure many of you have seen lots of beautiful pictures from this. This is the Herschel imaging survey of OB young stellar objects. The PI is Frédéric Mott at University of Grenoble in France. And this was surveying 15 molecular clouds that are relatively nearby, but still forming massive stars. So 0.7 to 3 kiloparsecs, so sort of the closer end of what Jim was talking about with the ramp survey. And they have amazing pictures showing all these beautiful and complicated things going on. So this is one example on the bottom here showing the Cygnus X molecular cloud. And in this particular region, you can see a lot of fine photoionization going on quite a wide range of scales. And that's clearly impacting where the dense gas is going to be able to form stars in the future. Some of the other interesting things that Hobbies as a whole has been finding is they don't see a lot of high mass starless cores. So that already suggests that high mass star formation is not completely analogous to low mass star formation. And tying into Jim's talk again this morning, where he was talking about these two pictures of how higher mass stars form, and this turbulent accretion model, which was kind of like a scaled up version of low mass star formation, where you start with these higher mass starless cores. That doesn't seem to be as supported by the data from Hobbies. And that again agrees with what Jim was talking about, using completely different lines of that evidence. And unlike in low mass star formation, there's plenty of dense gas, even not in the filaments. But there's a new population of higher mass per unit length filaments that the Herschel people like to call ridges. And then there's also these intersections of filaments called hubs, which may also play an important role for the accretion needed for very high mass star formation. Some of the Herschel papers from hobbies suggest that you may even start to need to form the low mass stars in order to drive the processes in order to be able to form the higher mass stars. So for example, in W3, which is the image I've got on this slide, Rivera Engram et al. Suggests this convergent constructive feedback model that really you need those first lower mass stars to start to push the gas around enough to be able to condense dense enough to get the high mass stars forming. But the really important caveat with all of these flashy Herschel results is that, there's a lot of models, hypotheses about what's happening with the dense gas, how the stars are forming out of it, but they're only using spatial information. So, you see dense cores on filaments, but we don't actually know the relationship between them when we're only looking at the dust. We really need to look at the kinematics, look at what the dense gas is doing in order to understand how is mass moving around, or how are these things actually tied rather than just they look like they're in the same spot. So that's really where Keystone got motivated to come in. So this stands for the KFPA Examinations of Young Stellar Object Natal Environment. The PI is James DiFrancesco, also here in Victoria at HAA. And the goal was to map ammonia in the hobbies fields that were observable from the GBT in order to obtain all this kinematic information that we need to fully understand and test these models of higher mass star formation. The goal was to focus on areas with ABs above 10 magnitudes, just in order to get stronger ammonia detections. And in all, the survey mapped 5 square degrees in a little over 350 hours from 2016 to 2019. The spectral setup is the same as ramps, which you've already heard about this morning. So basically the ammonia inversion ladder and then some other trace molecular species as well. So in total, there was 11 clouds mapped, going from about 1 to 3 kiloparsecs. So again, a little bit closer than the ramps clouds, but a little bit further away than the gas clouds. And these surveys are all very complementary to each other, as has already been talked about earlier today. So, gas is mostly focusing on the nearest star-forming regions, which tend not to be high-mass star-forming. Ramps does high-mass star-forming, and they tend to be further away, and then Keystone is covering this middle ground. And some of the clouds were covered a bit by ramps, but had areas that were outside of ramps that Keystone covered. So what does the data look like? Quite nice. So medium RMS between 0.13 and 0.2 Kelvin, and most regions have many of their pixels much below that value. So I'm showing you on the bottom 2 examples of fitted temperature and line width maps, also centroid velocity, all of your standard things that you fit with ammonia. And so these pictures on the bottom are showing you the thick black outlines, the sort of squarish parts are showing you the Keystone footprints. The gray lines you can kind of just see going wiggly off the top there are showing you where the larger Herschel map ends. And then the colored parts are showing the fitted property maps. And all of the data, including the fitted property maps, not just the reduced data, are publicly available already, giving you the DOI there, or check out Jared Cowan's 2019 paper on first look on all the Keystone results, which goes over everything in a lot of great detail. And I should stop and say that a lot of the slides that I'm going to be showing on the next little bit are all thanks to the hard work that Jared did. He's not in astronomy anymore, but he would have otherwise been very well placed to give this talk. He did a lot of great work for this survey. So it was a bit hard to tell from that last slide because the areas that were mapped are so big, but there really is this beautiful, rich data set for each of these observed regions. And so I'm focusing here on a region that was a bit smaller to be mapped so you can actually appreciate the Keystone data a bit better. So again, here's the Herschel hobbies map of NGC 2264, and then roughly matched to scale, there's the Keystone data, again, looking at kinetic temperature on the left and line width on the right. And you can see up on the top left-hand corner of each of these 2 slides, you can see the GBT beam. So you can see that we're getting many resolution elements and lots of structure going on in the data that will be interesting to try to understand. And so even just a very quick look at the pixels in all of the different clouds analyzed shows that there's quite a variation in behavior across these regions. So these are just ordered from typically smaller to typically larger kinetic temperature values. And you can see that MONR1, the cloud on the very top panel, has temperatures 10, 15-ish Kelvin. And then down at the bottom, M17 is kind of more 20 to 25 Kelvin. And again, on the right, you're seeing in that same ordering as on the left-hand side, it's showing you the line width, and again, quite a difference as we go through these different clouds. So we're tracing quite different environments in these 11 clouds. To do further analysis, there's a lot of different avenues available. We heard a little bit about this in Brian's talk earlier today too, but I wanted to talk to you about what Jared did for this first look paper, which was doing a dendrogram analysis. So probably many of you are familiar with this already, but the basic idea is you're kind of splitting up your emission map into a sort of a tree diagram. So in this case, we're just looking at the integrated intensity of ammonia 1,1. I'll come back to that in a minute. And what you do is you march down from the peak of the emission downwards, and you're looking for individual blobs of emission that you then can create this hierarchical dendrogram structure from. And the idea is that the top level structures, what they're called leaves, those are the things that roughly hand wavy speaking correspond to clumps. And then the other information is telling you about how they structurally relate to the larger scale emission in the clouds. Now I will emphasize that in this first look analysis, multiple velocity components were not considered, and I'll come back to that later. It is important for some of the regions, but for many of them, there seems to be one visually obvious main component of velocity, so it's roughly okay for many of the regions. So what do you do when you get that? This is again showing this NGC 2264 region, and all these neon green outlines are showing you where all these individual dendrogram leaves, which I'm just going to call clumps from now on, they roughly correspond to clumps, are found. And across all the regions, there's about 970 of these structures found. Jared went through and culled the ones for further analysis that didn't have great ammonia fits. So if we're trying to do something like a varial analysis, we want to make sure that we're confident in the kinetic temperature and the line width in at least some portion of the pixels within each leaf if we're going to do anything further with it. So that culled it down to 856 reliable leaves, and 835 of those have corresponding reliable structures within the hobbies data, which is needed to estimate the mass of all the sources. And the culling, I'll emphasize, is getting rid of things that are more likely to be noise peaks. So the bottom right-hand diagram there is showing you the tree diagram for NGC 2264. So those blue lines are showing you all of those main leaves. The red is showing you the connecting branches. And the black, which it probably is hard to tell that color difference, but I've pointed them out with the arrows. Those are the ones that got culled. And so you can see none of them are hooked up to anything red, right? They're all individual, isolated peaks that were identified, which is where you'd expect the noise to be coming in, where you'd expect noise peaks to be sort of isolated on their own somewhere in the map. And that tends to be where these things are getting culled from. So all of our interesting structures in the middle stay after the culling. Jared also ran some other structural analyses to really fully interpret what he was seeing from the Keystone data. And so there's a few different tools you can use for this. The first thing Jared wanted to do was to look at where the filamentary structures are. And probably many of you have probably heard of GET sources, which is something that Sasha Menchikov developed for the Herschel data, basically a multi-wavelength multi-size scale analysis for pulling out where dense compact structures are. He later developed some follow-up software called Get Filaments. And the idea is when you run all these packages together, you sift out the dense compact roundish things from the dense compact, or from the more elongated things, which he calls filaments. And then also the cloud structure is taken care of as well. And so running this software, you can see on the left-hand panel at the bottom, the black pixels are showing you roughly where the things that got classified as filaments were found in the Herschel data. And you can see some of them are sort of individual structures, and some of them seem to be more intersecting networks of filaments. And so Jared went through and identified, what's a single filament, what's an intersecting network of filaments. And then he classified the dendrogram leaves, which are shown as the red contours, as being either on a filament or off a filament. And if it's on a filament, is it just a single filament, or is it at one of these intersections of multiple filaments? And about half of the sources altogether averaged over all the clouds were on filament. Jared also, because there wasn't Herschel Hobbies published catalogs of the protostars in all of the Hobbies clouds when he was doing the analysis, he just ran his own version self-consistently across all the clouds. So he just looked at the Herschel 70 micron map and used the same method that Vera Konyev's used earlier to basically identify compact point sources that appeared to be protostellar. And that's shown in the right-hand panel with all the little red circles. And so overall, cloud to cloud, there's quite a lot of variation in how these leaves associate with these other structures. So overall, there's 34% of the clumps or leaves seem to be associated with protostars, but in MONAR 1, it's only 17%, and in W3 West, it's 58%. So you can see there's quite a range of things going on in these different regions. So going back to the dendrogram analysis now, one of the first easy things you can do is estimate a mass and a size for all of the leaves or the clumps, and that's what's shown on the left-hand plot here. Each cloud is color-coded with a different symbol, and the gray lines show the range of possible best fit lines that one could put through the data. The power law slope works out to about 2.5, and within the error bars, it could be mass goes as R squared or mass goes as R cubed. So somewhere between constant surface density and constant density for the leaves. On the right-hand side, I'm showing a plot that, again, many of you are probably aware of. Jens Kaufman and Tushara Pillai came up with this observationally estimated threshold for in-mass size space for where massive star-forming clumps tend to lie. That's shown by the gray shaded, I guess the white part is and the dashed lines show you what would be above this threshold, and the gray shows you what would be below this threshold in the Keystone sample. And so you can see most of the Keystone leaves are actually below the high mass star forming limit. But the green symbols, which are showing you leaves that are found at intersections of hubs and also things classified as ridges, a larger portion of them tend to lie above this. So they would be more likely to be forming massive stars. As we've already seen this morning from both Jaime and Jim's talks, another nice thing that we like to do with this data is run a varial analysis. So the first step is just the standard alpha analysis. So you're just looking at self-gravity and thermal and non-thermal motions within the object and seeing how they balance out. And again, the colors show you all of the different clouds. All the different color coded for all the different clouds. And what we're seeing here is quite intermediate between what we saw this morning. In the gas, we saw that most things were unbound, and in ramps, most things were bound. Here it's looking a bit more 50-50. It does vary quite a bit by region. So in MONAR 2, only about 30% of things are bound, and in M17 and W48, it's more like 90%. And I should say that M17 and W48 are some of the ones that are also partially in the ramp survey, so there is consistency there. Jared did a bit of work looking at the impact of distance, like if you put the closer keystone regions just further away and try to simulate what you would get in that case, you do tend to find things get a bit more bound as they get further away, just the nature of how you're averaging over larger areas, but that didn't seem to account for the entirety of the difference. So I think part of it is just the nature of the structures you're tracing. And just as a comparison, this is, Jaime showed this slide already this morning. This is from the gas data looking at some of the first release regions and comparing that with the right-hand side, what we see with Keystone. So a lot more things look gravitationally bound in Keystone. Interestingly, there was no obvious trend with leaves associated with filaments and leaves not associated with filaments, sorry, clumps on filaments and clumps off filaments. And so the speculation here is that perhaps in these higher density environments, you don't need filaments to provide dense gas. There's dense gas everywhere, everything's denser. And so they may be less required for star formation in general at these higher densities of keystone clouds. There were some trends with clumps associated with protostars and not associated with protostars. As you'd expect, the protostars tend to be a little more bound. You know, they have to be at some point. It's not as strong a trend as I might have expected anyway. So the bottom two plots are showing you, again, just for the NGC 2264 region. So on the left-hand side, you're seeing the lack of a trend with filaments. So the different colors tell you whether you're on a filament, off a filament, or with the hub or ridge. And you can see all the colors are distributed pretty equally, except of course the hub ridge ones tend to be very massive. And then the right-hand side is showing you the protostellar fraction, number of protostars, sorry, on each of these leaves. And you can see there's a slight tendency to more colored points towards the bottom right of the plot, but there's certainly colored points on everywhere and gray points everywhere on that plot. Next, we considered other sources of binding. Again, just as Jaime talked about this morning, this is sort of in this energy density formalism that Kate Paddle initially introduced. And the idea is how much more binding might I get from the overlying weight of the cloud or from other sources such as the ambient turbulent medium. So for the former, the weight of the overlying cloud, they just use the column density maps from Herschel and just take the large scale component of that to represent the overall cloud mass. For the ambient turbulent medium, some regions have C1803-2 data from JCMT HARP. So Jared just went through the archive to see what was there. And so for the subset that had it, he was able to make this estimate as well. And what he finds, again, somewhat analogous to gas, is that these additional sources of pressure do bind many more cores. And you can see that on the bottom left and on the bottom right. So basically, left to right is showing you unbound versus bound, and then top to bottom is showing you what's doing more of the binding. So things that are near the bottom are bound more by cloud weight on the left, or the ambient turbulent medium on the right, and then things on the top would be self-gravity is doing more binding. And just to remind you again, Jaime already put this one up this morning. Here's what's seen for some of the nearby regions in gas. As you can see, the overall distribution of points is somewhat different, but again, there's more points below that dashed line than above it, saying that in general, this pressure is doing more than self-gravity is doing. And I should point out that magnetic fields have not been included in these analyses because we don't have consistent maps for all the regions. So that would be another term to consider for a full varial analysis. Okay, so one other interesting thing that Jared did was said, well, if I've got I've got all these clouds, I've got all these interesting Varial related properties measured for each of these clouds. Do I see any correlations? And so this is just showing you a heat map of the correlation matrix for everything he thought to compare. Of course, that line of values of 1 across the diagonal in the middle, that's just things correlating with themselves. So that doesn't tell you anything interesting, and it's a symmetric diagram. The top and bottom are the same. And anything with a black line around it is showing you statistically significant correlations. Blue values are inverse correlations, and the red ones are positive correlations. And all in all, there's 8 properties that are statistically significant. So what are they telling us? Before I show you what they are, I'll take a step back and at the same time introduce sort of what we think they mean. And so this is a plot probably everyone has seen many times before. This is the well-known correlation between star formation rate and dense gas. This was the original Gallant-Solomon looking at HCN. And so that plays out in many of the correlations, many of the 8 correlations that Jared found. So a higher star formation rate probably means there's more protostars. So the plot on the top left is showing you the correlation between total protostars and dense gas mass. So that's probably where that one's coming from. You would also expect more ammonia leaves, more clumps, where there's more star formation and more dense gas going on. So protostars compared to ammonia leaves, equally, we just think it's star formation rate and dense gas correlation. That explains both of those. I already alluded to earlier that in the denser Keystone regions, there seemed to be less need for filaments to be forming stars. They seem to be able to form anywhere. And so the fraction of leaves that are on filaments, or clumps that are on filaments, seems to be lower for denser gas. And so if you take that inverse correlation and again just look at the relationships on the top, that gets you your other correlations that Jared is seeing. So dense gas versus leaf on filament, total protostars versus leaf on filament, and total number of leaves versus leaf on filament. The final possibly related correlation, but the statistics are kind of marginal, is that there's perhaps a trend between the median kinetic temperature in the region and the mass surface density. That seems to be mostly driven by that plot on the point on the upper right. So is that real? To be determined. And then finally, there's a few other correlations that aren't explained by the Gallant-Solomon one. One of them is probably driven by the well-known, well-expected thing that protostars, when they start turning on, they're going to unbind their surrounding gas through all the feedback, through outflows and ionization and everything. So this is showing a nice example from a fairly recent simulation, including Stella Offner, that the vertical axis is showing you the boundedness of the ambient gas in the simulation. There's 4 different magnetic field input start parameters that are showing you the different curves, and then as a function of time. And those 4 black stars are showing you when the first protostar turns on in each of those simulations, and you can see what's happening to the ambient gas thereafter, and basically roughly when the first protostar forms, and certainly immediately thereafter, much of the gas becomes unbound. And so with that, you might expect that if you have a higher fraction of protostars in your ambient gas, that you're going to have fewer bound leaves. So that's that plot on the top there. Seems to be perhaps an evidence of feedback in the regions. And then finally, this plot on the bottom is the last correlation seems to be an inverse correlation between the distance to the clouds and the surface density of protostars. And that's probably incompleteness because you're not able to see as many distinct lower mass protostars as you get further away. So the encouraging thing is this was the only correlation that Jared found with distance. So hopefully distance is not, and incompleteness related to distance is not a major factor in any of the other parts of the analysis. Okay. So what else is going on after Jared's beautiful first look paper? There's a lot going on, which is great. I think I saw Glenn was still online, even though it's quite late in the UK. So thanks, Glenn, for staying on. The first other work I wanted to highlight was Glenn White is doing some work with water masers. And there are very few wide field surveys of water masers that are out there anywhere, but they're very useful and important. Water masers are often associated with young massive stellar objects. And if you can pinpoint where they are, they can be used for follow-up VLBI measurements to get distances to star-forming regions, which is obviously vitally important for understanding most of our other measurements. So Glenn and his colleagues have been working on a maser catalog at W3. Some of the spectra are shown there on the bottom right. And the excellent angular resolution from the GBT is really helpful for identifying where the emitting sources are. The hobbies team is also using some of these results. So this is in W48, Stefano Pizzuto in Italy is right now, they're sort of doing a Herschel focus with ammonia thrown in the side. And then when they're done that, they're going to flip their considerations and do an ammonia focus with Herschel thrown in the side. So what they're doing right now is they're doing a careful analysis of all the dense objects they find with Herschel. And so for that, you need spectral line data to get a velocity to try to do some modeling. And W48 is partially covered by a high-gal spectral survey, but not everything. And so Keystone is providing velocities for 50 sources that would otherwise have no information about them. And there's also, of course, some sources that have both information from Keystone and the high-gal survey, which is, I'm forgetting now what molecules, but not ammonia, it's something else. And reassuringly, they generally give the same information. There's only one source that's wildly different, which is circled there in red. And Stefano thinks in this particular case, there may be actually two components of dense gas along the line of sight. And so Keystone is picking up one and high-gal picked up the other one. And there should be lots more interesting things to come on the ammonia side for this later on. In DR21, Lars Bahn is leading an effort at SOFIA, one of their legacy programs called Feedback. So they're looking in the infrared, they're looking at the carbon-2 and the oxygen-1 lines. And those are telling you about cooling from moderate density gas and photodissociations and warm high density gas. So Keystone with cold dense gas is really a very complementary view and very helpful to be putting together all the pieces to understand how these high mass stars are influencing their environments. So what you can see there on the bottom left, the color is showing you the integrated C2 map, and the contours are showing you the ammonia 1,1. And you can see they, by and large, don't line up, which is perhaps what you'd expect since you're tracing very different things. The right-hand two panels are showing you a comparison of the centroid velocities, again, from C2 and ammonia. The contours in the background are showing you the Herschel-derived column density maps. So again, not a lot of correspondence, which is probably useful for trying to understand how gas moves through various density phases. And this is what they're finding for the line widths, again, comparing C2 and ammonia. Again, quite different. And Lars told me that they're quite interested in regions like this, sort of on the edge of the higher column density area where the ammonia line widths tend to be a bit larger. And they think that that may be evidence of where the accretion, seeing this accretion of material from lower densities at the higher line widths down to the denser more quiescent gas that they see sort of at the center of the most dense regions in the center of DR21. So that's all work still in progress. There's a lot of work going on looking at multiple velocity components. So we've heard a lot about this from Brian already, and I'll get back to that in a bit. This is some work that an undergraduate, Ty Withers, is doing with Sarah Sadaboy at Queen's. And they are using like Chen's code and Mufasa to try to identify which spectra would benefit from having two or more. I think they're just doing two, actually, two velocity component fits, and then trying to look at similarities between neighboring pixels in terms of how these multiple velocity components are fitting. So Ty sent me this slide, and you can see they're finding, this is showing you the centroid velocity. The left-hand panel is showing you the first component fit, and then the second component fit is in the middle, and how that compares with the Keystone results are on the right-hand side. And so you can certainly see in that little blow up that's shown there from the middle panel that there's quite a lot of interesting substructures that they're finding with these preliminary fits. Of course, you can also do more complicated techniques, and we had a very nice talk from Brian this morning on what you can do with the Bayesian analysis. And he also highlighted a bit some of the work that Jared did with this machine learning code called Clover. And so, as Brian already mentioned, Jared really focused on two different areas within Keystone, one that tended to have a lot of visually obvious multiple velocity components, and then one that did not. So I'm showing you M17, which had a lot of these visually obvious velocity components. He compared two different fitting techniques, one using chi-squared modeling to make the predictions, and one using a convolutional neural network. And in general, anywhere where there's bright signal, the two methods agree pretty well on how many components are needed. It's only when you get into the very low noise areas that there tends to be a bit more disagreement. And of course, it's important to fit these multiple velocity components when you're doing things like a varial analysis, for example, because if there's two velocity components there and you fit it as one, you're probably getting your line width way too big. So that's what's shown on the right-hand panel here. This is showing you just for M17, the three leaves that were found, how this alpha versus mass plot changes when you use the one component fit used in Keystone, which are the blue points along the top. And then when you use Jared's Clover technique, you have two velocity components, and you can see that in every case, alpha goes down, things look more bound, because there's less line width associated with everything. And this is also going to be crucially important going forward with looking at things like how the mass moves within regions, looking at accretion onto filaments, motion across filaments. You need to disentangle all these unique velocity components before you can do that analysis properly. Keystone data has also been used for magnetic field analyses. So this is work led by Vera Konyevs and also, I'm forgetting the first name, Huang from Korea. And the idea here is that you get great polarization measurements from something like Pol 2 with the JCMT that tell you about the magnetic field orientation. But if you want to interpret those orientations in terms of a total field strength, typically one uses something like the Davis-Chandrasekhar Fermi method, and that requires some velocity information as well. And that's where Keystone comes in. So this is showing you one example here from the Rosette molecular cloud. You can see the polarization vectors rotated by 90 degrees to show you where the magnetic field is expected to be on the plane of the sky for the Rosette molecular cloud. And MONAR2 is also in progress. There's also lots of other future directions that can need to be tackled still. And there's, so for example, I have been talking a lot about kinematics and mass accretion. How is mass flowing from all these scales? What's the impact of environment? We certainly see that these clouds are behaving very differently, but we can look at that a little more systematically. Looking at the dynamics of dense substructures, particularly at the intersections of filaments. That would be a very interesting place to see what's happening with material moving. Ammonia chemistry across environments, like Jaime was highlighting this morning with gas, so that hasn't yet been tackled for Keystone. I told you about the water maser census, and of course, high resolution follow-up of interesting regions. There's a bit of that ongoing as well, which I didn't highlight here. So just to wrap up, Keystone has been a great success. There's a huge wealth of information about the kinematics and the temperatures of dense gas associated with these nearby high mass star forming regions, where we can get slightly better angular resolution than ramps in some cases, but perhaps not tracing quite as vigorously high mass star formation as that survey. All the data and the model fits are publicly available already using that address. Jared Cowan published a really substantial first analysis. I encourage you all to look at that paper if you're interested in more detail, including the identification of compact structures, the association with Hobby's data, looking at clump masses, protostars, filamentary structure, Varial Analysis, just self-gravity versus pressure, including external pressures, cloud-to-cloud comparisons, and then works in progress include masers, kinematic distances, infrared comparisons, multiple velocity components, and there's so much more to be done still. It's really exciting to be involved in this project. So that's all I have to say for now. Thank you, and I'll take questions.
Sorry.
Hey, Helen, thanks. I'm really interested in this on-filament, off-filament identification.
Yeah.
So if I understand correctly, you have a leaf.
Oops. Yeah.
That is a pool, let's say, of gas, dense gas, and then the sources you're calling on-filament or off-filament are these 70 micron Herschel sources, right?
No. So the on-filament, off-filament is whether the extent of the dendrogram is on one of those filaments that get filaments identified, or whether it's off somewhere else. Let me see if I can find that slide again. Not that one, this one. So what you can see on that bottom left figure there is the black is showing you where get filaments is saying these are pixels that are associated with the filament spine. The red is showing you the outline of where the dendrogram leaves are from the ammonia. And so I think I don't remember Jared's exact criteria, but I think it was basically if most of the pixels from the dendrogram leaf are lying on the filament spine, as you know, are lying on those black pixels, then it's on filament, and otherwise it's off filament.
Okay, thanks. I misinterpreted that.
Yeah, Tony?
So do you have to be on a filament to be bound or not?
No, that was the surprising thing, was there was really no no correlation between on or off a filament and boundedness. We were expecting to see something because that's sort of the picture that's been painted by the nearby star forming regions, but that wasn't the case for this.
Okay, that's okay. That clears up, because I missed that, but or at least I heard that. I'm like, I just want to make sure I heard that correctly.
The questions coming in over Zoom.
Yeah. Yancy, if you want to go ahead and mute yourself.
Hey, Helen, I hope you get feeling better soon. Thank you for doing that. Yeah, I had a question from Jared's paper, and I should probably remember the answer for this, but I don't. But the really interesting plot about the bound leaves fraction versus the number of protostars, it was right after you showed Stell Offner's theoretical results.
Yeah.
Yeah.
Oh.
So what I was curious about, so right after that, I think
I'm gonna have to go to play again. Sorry.
Oh, sorry about that. Yeah.
No, that's okay. There we go. There. Yeah.
So I think that, that upper left diagram with the like surface density of protostars or number of protostars. So it's kind of curious. I'm trying to remember, is the bound leaf fraction including the external pressure and determining boundedness here? Because I was trying to reinterpret this diagram and think about it. If you have more turbulence from the protostars, yes, that increases the internal kinetic energy, but also in theory, it would also increase the pressure bounding outside, because that stuff goes outside the clumps and stirs up the gas. And so you have this very you could have also more squeezing potentially from turbulent ram pressure. So I'm just curious
Um,
about the interpretation of that and what exactly meant by bound leaf fraction here.
Yes, good question. I can't remember if, I can tell you for sure that the turbulent medium binding is not included because that CO data didn't exist for every leaf. It was only a biased subset. So for all the subsequent analysis, Jared didn't want to limit to only the portion that had the CO data needed for that turbulent binding term. So he wouldn't have used that. I don't remember off the top of my head whether he used the cloud weight binding pressure or not. I don't think he did. I think it was just from the initial alpha analysis, just self-gravity and internal motions, but I would have to double check that.
Good, thank you.
Yeah.
Other online? Pedro?
Don't see anymore.
Okay. Any question here from Larry?
I'll go again. So back to the on filament, off filament. If I'm now interpreting this correctly, it's almost a measure of the correlation between the ammonia and the dust continuum. Is that right? Spatially, anyway.
Yeah, that's a good question. I haven't looked enough at the Herschel maps of these regions to give you a definitive answer on that. So what I'm not sure about is there could be quite a lot of Herschel emission that's just not very elongated, in which case it wouldn't get picked up as a filament like at filaments.
Right. I need to go back and look at the paper again. Yeah.
Yeah. So I would need to go back and double check that. I'm not sure at the longer wavelengths with the denser Herschel material whether how much is in filaments versus not for some of these regions.
Thanks.
Any other questions, locally or online? Well, if not, let's thank Helen again.